Alright, so this is my video on the proof of the Brouwer fixed point theorem from our book, page 392. There is the theorem. If you want, you can pause it and read it now. I'm not going to read it out loud. But I'm going to give a proof that's kind of derived from the one in the book, but a little different. So it's on here so you can pause it if you need to think about it or go back. So hopefully you'll find it helpful. Alright, so suppose we take this, we have this blue disk like it said, and then suppose we had the red disk was folded and say an arbitrary plopped it on there, and let's say it looks like this. It's all folded up, and there's kind of a reason I did that, but this argument will work for any way I would have put the red disk on there. So suppose we have a compass that we put around the edge of the blue disk, and it points to, so this compass, the arrow points to where the matching point on the red disk was. Because again, at the beginning we had this blue disk, and then we had a red disk right on top of it, right? And we corresponded all the points. That was our original correspondence. Right, so all the blue ones, remember the red ones, they were touching. Alright, so this compass, so this point here on the edge is pointing to, it's going to be pointing in that general direction because the whole red disk is there. Alright, so we basically do this for every point on the edge of the blue disk. And we keep going around, and we want to keep track of how many times that compass arrow is going to go around the compass. So as I'm drawing, think about that. How many times is the arrow going around the compass? Alright, and it starts out kind of pointing at 5 o'clock, and then it's going clockwise, and it's going to get back to 5 o'clock. Alright, so the arrow goes around one time as the compass goes to every point on the edge of the blue disk. Alright, so we give a name, that's called the winding number. I'm going to use this. So the winding number when the compass is on the edge of the blue disk is 1, right on the edge. So now, let's see if I can do this. Yeah, so now let's suppose we have, we just bring it in a little bit. So I won't draw this because it'll get too messy, but suppose we bring the compass in just, to the next set of points inside. Right? So you can see that winding number is still going to be 1. Right? So the winding number is 1. Right? Just inside the edge. Right? So that's pretty important. So we get a winding number of 1. So now let's do our blue disk again, and do our crumpled red one again here. And now let's go more towards the center. Alright, so let's say the center is here. Didn't show up. So now our compass here, let's look at our compass again. It's going to point to the matching points on the original correspondence up here. Alright, so you can see there is going to kind of look like this. It's going to be pointing as we go around. And if you look, it starts out at 1, it goes closer to 12, and it pretty much stays about at 1 o'clock. So here, the winding number is 0, right, at or near the center. that's important. The key thing, it's different. Right? So it's different than if it was on the edge. So, so again, this is for this red distortion here, plopping it back on. But we'll talk about how it's the same no matter what the red distortion is. Um, so now we got to kind of think about the circles, not at the edge. Right, there's the ones at the edge, and not at the center. But what about in between? All right, so somewhere, since it was 1 on the outside and 0 in the middle, somewhere the winding number had to change from 1 to 0. Alright, so think about that. But like we talked about up here, right, if you just keep bringing it in, it's never going to change, because if you just think about, bring the compasses into the next point. So if you keep bringing it in, the winding number is still going to be 1. Like think about it bringing it in from the inside, or even, from the perimeter, bring it in. The winding number, every little movement in, it's always going to be 1. Right, and from the center, start moving the compasses out as the compasses get wider and wider circles here. Right, the winding number is still going to be 0. So somewhere it has to change. All right. Well, the only way for it to do that is if the winding number doesn't exist. All right. So this basically shows that somewhere the winding number doesn't exist. All right. So in other words, the compass doesn't know where to point. All right. So on one of these circles, the compass is going to get to a point where it doesn't know where to point. So if you think about it, if the compass, for this picture, it's going to probably be around here. The compass isn't going to know where to point. The reason it's not going to know where to point is because it is directly above, the compass is directly on the point where the original red and blue match. Alright, so the winding number doesn't exist. Right, that only happens when the red point is directly above the original corresponding blue point. Alright, so in other words, there's a fixed point. There must be a fixed point, at least one. Again, just kind of in summary here. Alright, the compass, if you move in from the outside, every little movement, the winding number is 1. Alright, from the center, moving out, the winding number is always 0. So at some point in time, the winding number is going to change. And the only way for the winding number to change is if the compass doesn't know where to point. Alright, because here the arrow doesn't make a full circle around. Up here, it does make a full circle around. So at some point in the time, the compass isn't going to know where to point. And that's going to happen when the compass is right on the point where the original red and blue one match, right? That's what a fixed point is. So essentially that proves that there must be a fixed point. And it's a pretty important theorem. We'll talk about it more in class. But yes, please bring questions to class, specific questions about what you didn't understand here if there wasn't anything, and I'll be happy to discuss it in class. All right.